So the thing when you're doing scale models and scale diagrams is, you always keep in mind is, it's the scale factor, the scale you're given is the representation to reality. Okay, so the representation could be a drawing. So it's a unit on the drawing is so many units on the real thing, right? It could be a model, right? It could be a model airplane or something. And again, the scale factor is something on the representation to something for real. So a model for an Airbus 380 is a scale of 1 to 144. So this is 1 on the model is 144 on the real plane. Okay, the actual plane. And that's 1 unit, right? 1 foot on the model would be 144 feet on the real plane. 1 millimeter on the model would be 144 millimeters. 1 centimeter would be, and so on, right? So there's no units with the scale factor, right? It's 1 of these is 144 of those. Now, if we take a look at the plane, we can see the wingspan is 79.8 meters. That's the real thing. And we want to know what would the wingspan be on the model. So the way we're going to set it up is by saying, okay, I want to know, well, I've got a scale factor of 1 to 144. And remember, this is on the model, this is on the real plane. On the real plane, so this real plane is on the bottom, so this is 79.8. And on the model, we'll have an X. Okay, so we just have to set it up. You have to realize, what measurement do I have? I have a measurement on the real thing. That's going to go on the bottom. So we cross multiply. We get 144x is equal to 79.8. Now, well, let's do the calculation. So x is 79.8 over 144, which is 0.55. Now, the 79.8 was in meters, so when we get that 0.55, it's in meters. Okay, and we could say, or on the model, we could say 55 centimeters, right? So wingspan of the model will be 55 centimeters, so fairly decent size model. And we want to do the length. So the length is 73 meters. Again, we set it up, right? So it's model to real life is equal to model to real life. So 1 over 144, right? 1 unit on the model is 144. Since this is meters, this has to come out as meters as well, right? So again, 144x is 73, cross multiply. X will be 73 divided by 144, which is 0.51 meters. Okay, now it's meters because this was meters, right? Remember, there's no units here. 1 over 144, there's no unit. To have no units here, they both have to be in the same units, right? So we get x over 73, and they'll both be in meters. Or 51 centimeters. Okay, so if you're looking at your model, it's going to be about yay long. And the height is 24.1 meters. So again, 1 over 144, x over 24.1. Okay, so 144x is equal to 24.1, x 24.1 divided by 144. So x is 0.17 meters. Right? Because it's got to be in the same units this was in, and then we could change that. We could say it's 17 centimeters, right? Multiplied by 100. Turn meters into centimeters. Okay, so just remember, anytime you get the scale factors, it's the representation to reality. Front and side elevation of a pipe are shown on graph paper. A scale of 1 to 8 was used to draw the elevations, measure the drawing, and then determine each of the following dimensions for the actual pipe. Okay, so we're going to have a lot of time because we've got to get through 2 things. I'm going to give you the measurements. So this measurement is 5.5 centimeters. And if we go down here, the inside diameter is 2.6 centimeters. and the thickness of the wall is 2 millimeters. Okay, and we want to work these things out, right? So this time we have measurements on, we've got a scale of 1 to 8. Okay, so 1 unit on the drawing represents 8 units in real life. And outer diameter, okay, so we got to figure this out. The outer diameter, so outer diameter would be measured from here to here. What would the outer diameter be?
You just add the
3 centimeters.
Yeah, why 3 centimeters?
Plus 2 millimeters.
Yeah. Okay, so we've got 2 millimeters here, 2 millimeters here, right?
Alright.
So this is 26 millimeters, 28, 30 millimeters, or 3 centimeters. Okay, now it really doesn't matter. If we use 30 millimeters, then when we went up here, we would just, whoops.
It happens every day.
I know. Hey, but it got rid of the microphone thing. Didn't do it. Go. No, that's the wrong thing.
It's not good.
Oh, hang on. Okay. So 1 over 8 is equal to, so this is drawing, this is reality. So on the drawing, we have 3 centimeters, and in reality, we have x. Okay, so 1 times x is equal to 3 times 8, so x is 24, and that's going to be in centimeters, right? So we're using centimeters to measure. Inner diameter, so really we're just doing the same thing each time, right? Inner diameter is 2.6 centimeters. 1 over 8 is 2.6 over x. So x is 8 times 2.6. I mean, in essence, we're really just scaling up the drawing by a factor of 8, right? Just multiply everything by 8, and you're going to get the real life. So if that's 2.6 centimeters, excuse me, 8 times 2.6 is, what, 20.8, I think? 20.8. The wall thickness of the pipe, 1 over 8. Now, in this case, if we use 2, we're using millimeters, right? And this leads to x equals 16 millimeters, or 1.6 centimeters. Okay, so your choice. So if you choose to use the 2 here, you just have to realize this is millimeters, so x will be in millimeters, right? And otherwise, you could have put this down as 0.2 centimeters. And then the length, which was 5.5, 1 over 8 is equal to 5.5 over x. So x is 44, right? 40 centimeters. Okay, and in essence, the scale factor of 1 to 8 just says you're scaling it up by a factor of 8, right? If we do a scale factor of 8 to 1, then we're scaling it down by a factor of 8, right? If the first number in the scale factor is greater than 1, then it depends on the second number. You could have 3 to 5 or something like that. Okay, objects are considered to be similar if they have proportional dimensions, right? So whether it's objects or pictures or that, right? You can take a photograph, you can blow it up to different sizes. It's still, it's nothing stretched, right, out of proportion. So we keep it proportional. Determine the value of x and y if the 2 tetrahedra shown are similar. Okay, so we have the big one, right? This is big. This is small. And we've got one dimension in common, right? So we know that 50 on the big one corresponds to 10.25 on the small one, right? So that's going to give us, we could get a scale factor out of there, but we're really just asked to find what's x and y. So if we set it up as 50 over 2.5, that's big is to small, then we've got these sides correspond, right? And the big, okay, big, small, you got to put big here, 8.4, and small goes down here. Right, so just keep your proportion the same. Big is to small as big is to small. gives us 50y is equal to 8.4 times 10.25, and y is equal to 8.4 times 10.25 divided by 50. So really, the 10.25 over 50 is really your scale factor, right? And you're just multiplying the 8.4 by that scale factor to get the number. So y is 1.722. Now, what units would go with that? Millimeters, right? Because everything's in millimeters, okay? So these guys, especially these guys, have to be in the same units. Okay, maybe this is 10.25 centimeters. We say, well, this is the small one. No, it's not. It's actually bigger than that, right? That's 50 millimeters. If this were centimeters, it would be bigger. Okay, now, same thing. I want to find x. So we can do the same deal, right? We've got the 50 to the big, 50.00 to the small. 10.25 is equal to the big, in this case x, to the small, which is 9.15. Okay, in this case, we're actually scaling up, right? Because we want to get x, which is larger. And this is really your scale factor, right? 50 divided by 10.25. If you're scaling up, and the 10.25 divided by 50 is your scale factor if you're scaling down, right? It's about 1/5, right? I mean, you can roughly approximate. Well, that's around 1/5. So if that's 8, it's going to be about 8 divided by 5. Okay. I don't think I have. Is it this period that you were given? Sorry, I wrong. What was it? Let me just take a quick look. So let's solve this. So cross multiplying, we get 10.25x is equal to, actually you don't really need to cross multiply, right? You just say I want to get the x by itself, multiply both sides by, excuse me, 9.15. So 9.15 times 50 over 10.25. And what units is x going to be in? Still millimeters, right? So 44.63 millimeters. All right. Excuse me. So I'll give you a moment to copy that down. So in general, if two 3D objects are similar, and the scale factor for the two objects is k, really, I mean, this applies to 2D objects as well, right? K is equal to the linear measurement of the, so it's the representation over reality, right? So the scale model divided by the corresponding linear measurement of the actual object. To determine the dimensions of a scale model, given a scale factor of k, all of the object's dimensions must be multiplied by k. Okay, so the linear measurement of the scale model is equal to k times the corresponding linear measurement of the actual object. If k is between 0 and 1, then the scale model is smaller than the original object. And if k is greater than 1, then the scale model is larger. Okay. So sometimes we make larger models of things because they're too small. They're too small to see. So we blow it up, right? We make it larger and then we can handle it. So you may have seen that. Here's a scale model of you know, the inner ear or something, right? I mean, those are tiny little things, so they're gonna scale that up. Scale model of a car is 1 to 25. The diagram, excuse me. I pity anybody listening to this. Scale model of a car is 1 to 25. A diagram of the model along with measurements is shown below. Determine the dimensions of the actual car. Okay, so we got 60 millimeters wide, 140 millimeters long, and 75 millimeters high. The scale factor is 1 to 25, so the real life car is how many times larger than the model? 25 times. Okay, so all we gotta do is multiply everything by 25, right? So the length is equal to 140 millimeters times 25, which is 3,500 millimeters, or 3.5 meters. Right? I mean, interestingly, does anybody know if you see some building plans for a house, do you know what units they use? They use millimeters. Yeah. So let's say stuff like this length is 3,000 millimeters, right, which is 3 meters. But it means they can be very accurate then, right?
Yeah.
So you can say it's 1,270 millimeters, and you're not getting confused with converting back and forth, which, I mean, the metric is pretty easy, right? But you don't want to see all these measurements of 1.258, right? It's better to see 1,258. Just realize, hey, those are millimeters. The width is 60 millimeters times 25, which I think is 1,500 millimeters, or 1.5 meters. And the height is 75 millimeters times 25, which is equal to 1,875 millimeters, or 1.875 meters. And we know to convert from millimeters to meters, you divide by 1,000, right? Okay, scale factors, volume and surface area of 3D objects. Okay, so this basically is finishing off the course, right? We're done. Tomorrow, come in, you can work on any of the homework, review stuff, and that over the break, review. I put a final review up. I sent you a text, I think. Yep. Put a final review up on Schoology, so it's a PDF. You can print it out at school, print it out at home, whatever you like. You can use that as your review for your third Q, and also for the final exam.
How long is it?
How long is our periods tomorrow?
Yeah, I don't know. It ends at noon.
It's not very long.
We'll figure out what.
How long is it?
A lot of pages.
A lot of pages?
A lot of pages. Lots of review there. Okay.
Say
All right. So review of scale factors and areas. So we know we did this yesterday, right? So a 2D shape, like a rectangle. Let's say this shape has an area of 450 square meters. Scale, bless you. Scale factor is 1/3. So is the scaled area bigger than the original or smaller? Scale factor is 1/3.
Oh, smaller.
It's small, right? You're gonna have 1/3 of it. Okay, so this is smaller. Okay, so the scaled area is smaller. What is the scale factor for the area? So if the linear scale factor is 1/3, the area scale factor is, what do you do to the linear scale factor? You square it to get an area scale factor, right? So the area scale factor is 1/9. So what will the area of the scaled shape be? One ninth times 450, right? So it's 1/9. Okay. Anybody been to Paris to see the Arc de Triomphe? Okay, well, you've probably seen pictures of it.
Yeah.
There's a scaled down version of that in New York City in Washington Square Park. Scaled down model, right? Scale, right? 2D shape is a circle. All right, now what we know is that the area of the original is 60.8 and the scaled area is 15.2. So what can we figure out from that?
Divide it by 60.
Oh my God.
Oh, you moved it again.
I know, but I moved it back. Okay, so what's the scale factor? The area scale, so we have 60.8 is the original, so is it bigger? So it's obviously smaller, right? So it's smaller by a factor of what? What number goes in here?
When you just
1/4, right? 15.2 is 1/4. So what's the linear factor? If the area factor is 1/4, then the linear factor is 1/2. What do you do to get from here to here?
square root it.
You square root it. Here's a triangle. How do you want to work this? So the scale factor is 9/25, and the scaled area is 1,250 square feet. So if it's 9/25, is it bigger or smaller? If it's 9/25 the area of the original, it's got to be smaller, right? So this is smaller. So it means that we took 9/25 of something was 1,250, right? So what was the something? What's the original area? Well, that's the scale factor. So the linear scale factor is the square root of the area scale factor, right? It was scaled. The area was scaled by a factor of 9/25. And what is the 35.4? Well, let's do this. So x is equal to 1,250 times 25/9. Let's try that. What do we get? $3,472.2. Okay. What units? Square feet. Okay. Square feet are the units, right? Okay, so again, the takeaway, which was yesterday's takeaway, right? If you have a linear scale factor, you square it to get the area scale factor. If you have an area scale factor, you square root it to get the linear scale factor. And if this is the scale factor, then you take that times the original area to get the scaled area. Volume and scale factors. Okay, volume. Find the volume. What's the volume of this prism? So what's the formula for volume of a prism? Length times width times height. Okay, which is what?
384.
So 12 times 4 times 8, which is how much?
384.
384. Units?
Centimeters cubed.
Centimeters cubed. Okay, so before we go into the table, let's just kind of do this deductively. Right? The table is kind of inductive, right? The table will be, hey, let's try doing all these changes, see what happens, and then come up with an idea. Let's see if we can come up with the idea before we go in and do that. So let's say that we triple the size, right? So we're going to triple it. Triple the size. Then, now forget the numbers, right? So what's the volume? So the new length is triple L, right? 3L. What's the new width? 3W. And what's the new height? 3H. Okay, so we get 3 times 3 times 3 times L times W times H. Now that's the original volume, right? LWH. So that doesn't change. But it's being scaled by a factor of how much? So when I triple the size of the object, what do I do to its volume? It increases by a factor of 3 cubed, right? Because you're multiplying, right? So with area, we just have two dimensions, right? Your length and a width, or you got that radius squared. So if you triple the length, you triple the width, you end up with 3L times 3W, or 9 times LW, 9 times the original area. When you've got three measurements you're tripling, then it's 3 times 3 times 3, or 27, right? Okay, now let's go through the table. Okay, so if I scale it by a factor of 2, then the new length is 24, the new width is 8, and the new height is 16, right? So what's the scaled volume? What's 24 times 8 times 16? 3,072. And it's going to be centimeters cubed, right? These are all centimeters. The original volume, so the scaled volume over the original, so what's 3072 divided by 384?
8.
You know, 8 is 2 cubed, right?
Yes.
So when you cube the scale factor, right, and if you take, so if we know that if we're doubling each of the measurements, then the volume's going to increase by a factor of 2 cubed, right? If we're tripling, like we did here, it's 3 cubed. So if we take 8 times the original volume, we get the new volume, right? Okay, what if I quarter it, scale factor of a quarter? What do you think the, well, let's just do it. So quarter of 12 is 3 centimeters, a quarter of 4 is 1 centimeters, and a quarter of 8 is 2 centimeters. 3 times 1 times 2, I don't think we need to break out our calculators. That's 6 cubic centimeters. The volume, so what's 6 divided by 384? Now what you're going to want to do is go math, enter, and get it as a fraction, right? The scale factor should be fractions.
1/64.
1/64. And what's the cube of the scale factor? 1/64, right? Okay. So we don't need all of this, right? If I say if you're scaling an object by a factor of 1/4, its area will be what? Area now, not volume. So if your scale factor is 1/4, the area will be what fraction of the original? Wasted 3 days. If I scale an object by a factor of 1/4, its area is scaled by a factor of? Somebody say it, come on. Wow, 3 days down the drain. 1/16, right? And its volume is scaled by a factor of 1/64. Oh wow, 3 days just gone.
6.
Okay,
Oh my God.
they came together. Okay, if we do the same with a sphere, right? So that works with a prism which has 3 dimensions, right? A length, a width, and a height. And so when you triple each of the dimensions, right? But what happens with a sphere? So what's the volume of this sphere? So 4/3 pi. What's the radius? 4. Good. Okay, well, there's hope yet. Again, what we want to do here when we're comparing with the sphere is want to keep the volume in terms of pi, right? So we're going to get a number, so 4/3 times whatever 4 cubed is, which is 64. So that'll be 256 over 3 pi. So 256 over 3 times pi. Okay, let's go into the table below and see what happens when we scale this sphere up. Scale factor is 3. The scaled radius will be, so the radius was, so let's r is equal to 4 centimeters. So if I scale by a factor of 3, what's my new radius? 12 centimeters. Volume will be 4/3 times 12 cubed and pi, right? 4/3 pi times 12 cubed, which is, again, we just want to get this as a fraction of pi. So, need a calculator. Bracket 4 divided by 3 times 12 cubed. 2,304. So 2304 pi. Original volume was 268. Now the original volume was what? 256 over 3 pi. So scale volume 2304 pi divided by 256 over 3 pi. So the pi's cancel. I just want 2304 divided by bracket 256 divided by 3. Right, we get 27. See, and that comes out exact because I'm not rounding stuff, right? I'm just using the pi, using that. So when you're going to put that into divide, go 2304. 2304 divided by, well, in your calculator it's going to be a slash, and then go bracket 256 divided by 3. Okay, make sure that you get the stuff done. The original scale factor was 3. The scale factor cubed is 27. You note that these are the same. And I could take 27 times the original volume, which was 256 over 3 pi, and then 3 goes into that. That's 9. 9 times 256 will be 2304 pi. Scale factor is a half. The scaled radius will be a half of 4, which is 2. The volume will be 4/3 pi times 2 cubed. I don't need this anymore. And it's 8, so it's 32 pi over 3. The original volume, forget that, it's 256 over 3 pi. 256 over 3 pi. So I could take the original scaled volume, which is 32 pi over 3, divided by 256 pi over 3. Times, I can flip this, right? Pi down here. Okay, so 32 pi over 3 times 3 over 256 pi. Pi's cancel. 3's cancel, just leaving 1's behind. So we get 32 over 256. 32 divided by 256. And I want that as a fraction. Math, enter. And we get 1/8. Scale factor cubed, also 1/8. And the new volume, which is equal to the 32. So 8 goes into 256 32 times. Okay, and we keep everything nice and exact in terms of pi. So the takeaway, which didn't stick from yesterday, but hopefully, right? You have a linear scale factor. If you're then going to scale area, you square the linear scale factor. That gives you the area scale factor. If you're going to take a linear and square and compare it to volume, right? So linear scale factor, you square it to get the area scale factor. You cube it to get the volume scale factor. If you have the area scale factor, you square root it to get the linear. Let's say I had the area scale factor and I wanted to know the volume scale factor. Take the area scale factor, square root it. You now have linear. Take the linear scale factor, cube it. You now have volume. If you want to do volume to area, take the volume scale factor, cube root it to get linear, square that to get area. Okay, so they just work, right? Always go back to a linear, and then you can take it up to area or volume. Okay, so if you're given a linear, that's great, but if you're given area, square root it to get linear, and you want volume, then you cube it. If you're given volume, cube root it to get linear, then square it to get area. Okay, so it just flows along. Both tables, they're the same, right? Usual answer. They're the same. Next. Determine the volume of the trapezoidal prism shown. Okay, any figure that has a constant cross-sectional area, in this case the area of this is always a trapezoid, the volume is the area of the base times the height. The area of the base is that cross-section, right? The cross-section that goes all the way through. So it's a trapezoid. And the height here is the distance between the front and the back face. So this guy here is H2, and this guy here is H1. Okay, H1, given the trapezoid, is the distance between the parallel sides. I think we did this one yesterday. That's 40 degrees. This is a 90, that's opposite hypotenuse. So sine theta is opposite over hypotenuse. The sine of 40 degrees is H1 over 7. H1 is 7 times sine 40 degrees. Okay? Now I'm not even going to put that in, I'm not going to work that out. I don't really, it doesn't say find H1. I don't need that. I just need to put it into my calculator when I'm doing the calculation. So volume is 1/2 H1, 7 times sine 40. Make sure your calculator is in degree mode. A plus B, these are the parallel lines, so 10 plus 18, and H2 is 20. Okay, fire that into your calculator. Exactly the way you see it. Okay, and then let's round it to the nearest whole number. Okay, so just put it in exactly as you see it with all the brackets the way you see them, as long as your calculator's in degree mode, and rounding to the nearest whole number, and we get a number which is yet to be determined, but will be soon. 1,260? I don't know. 460 or 260? 260. I'm hearing more 260. 1,260 units. Okay, units are centimeters cubed. Okay, because it's volume. If a scale factor of 3 is used to draw a new trapezoidal prism, then the new volume is, so what do we do? 1,260 times what? 3 cubed, right? We take the scale factor, which is 3, that's linear, right? You always better be able to go to a linear scale factor. So if you're given a volume scale factor, you cube root it. If you're given an area scale factor, you square root it. If you're given a linear scale factor, you don't do anything. It is what it is. Okay, and what do we get? 1260 times 27? 34020. 34020. And still cubic centimeters, right? And then we don't have to sit there and go, well, this is 54, and this is 30, and this is 3 times, that's a 21 now, and that's a 60. You could do that and work it out, right? Like, you don't actually believe, I don't believe that's 34020, right? Then you could take all these guys and make this 54. Just go through. You're going to triple this, triple this, triple this, triple this. Okay, in general, if the dimensions of a 3D shape are multiplied by a scale factor of k, then the volume of the scaled shape is equal to k cubed times the volume of the original, right? Or k cubed, just rearranging, we're going to take this, put it under there, so it's the volume of the scaled shape divided by the volume of the original shape. Okay, that gives you k cubed, right? So it's possibly we give you those two volumes. You divide it out to get the cube of the scale factor, which you then cube root to get the linear scale factor, which you then square if you want an area scale factor, right? So you got to read the question, figure out what are they asking me to do, and so what do I have to do? Okay, complete following table. You got a sphere. Its volume is 900. The scale factor is 4. What's the scaled volume? Okay, so we got to cube the scale factor, right, which is 64. And then we go 900 times 64. All right, let's save you a little calculator work, which you will need to do on the next page because I don't have a key. 57,600 centimeters cubed. Okay, watch your units, make sure the units are in there. Rectangular prism. So it was 375 and now it's 3. So I've scaled it down by a factor of how much? How do we figure this out? We have two numbers, 3 and 375. What are you going to do with them? Add them, subtract them, multiply, divide?
Divide.
Divide. Okay, in which order? 375 divided by 3 or 3 divided by 375?
375 divided by 3.
No, that would be scaling it up.
It'd be 3 divided by 3. Oh, I thought
Math.
So the object was scaled down to be 1/125th the volume. So what's the scale factor, the linear scale factor? That's what I would do. You know what to do, I just don't have the tools to do it.
Wait, so you just cube?
1/5. Okay, so remember, here's what you've got, right? Because you know the volume, so just go back a page. So K cubed is the volume of the scaled over the volume of the original, right? So we've got scaled over original, 3 over 375. That's scale factor cubed. Take the cube root of 1 over 125 is 1/5, right? So you shrunk each dimension by 1/5, and you did a number on the volume, right? Like, I mean, it's a lot less. Okay, remember, it's the cube. So volume scale down or scale up a lot, right? I mean, areas scale up just by the square. Okay, I got a volume of 2. My scale factor cubed, this shouldn't be 64 cubic feet. This should just be 64. So if the scale factor cubed is 64, what's the scaled volume? Just 2 times 64, right? Which is 128. What's the scale factor? So if you got a scale of 64, then if your volume scale factor was 64, what's your linear? What do? You cube root it. 4. Okay, so you just got to figure this out, right? Over the break, right? Volume scale factor, area scale factors. Part C, surface area and scale factors, right? So just going back to surface area, kind of put it together. Remember, the area of the scale shape is k squared times the area of the original shape, or k squared is the area of the scale divided by the area of the original, right? So what's going to happen? You're going to be given enough information to either figure out k or k squared or k cubed. If you've got k squared or k cubed, you can figure out k. And if you've got k, you can get k squared or k cubed, right? You just move along this continuum of area scale factors, volume scale factors, and linear scale factors. Okay, if the dimensions of a 3D shape are multiplied by a scale factor of k, then the scale shape is k squared times the surface area, or take this divide. So you take the scaled over the original. Okay, so if you get two areas, you take the area of the scale divided by the area of the original, and that gives you the square of the linear scale factor. Okay, so we're going to do the 3 possibilities here, right? Got a surface area of 200, and I'm going to scale it by 4, which means the area is going to scale by 16, right? Square of this. And the scale shape would be 16 times 200, which is 3,200, right? The units are square centimeters. Okay. I have the original is 50 and the scaled surface area is 10, right? So what's the square of the scale factor? So how did we get 10? We had to go 50 times something is equal to 10. Remember, the something, the square of the scale factor is the scaled area over the original area, which is 1/5. So what's the linear scale factor? Square root of 1/5. Okay. That's all we could do, right? I mean, we can round it and that, but if we want it as an exact value, and for now I would prefer exact values, just go, okay, it's the square root of 1/5, right? Tetrahedron. It doesn't really matter what the shape is, right? I mean, the shape is immaterial. Your surface area is 2, and the square of your scale factor is 81, so what's your new surface area? So 2 times 81, 162, right? Remember, the scaled surface area is just the surface area times the square of the scale factor. What's the original scale factor? Just go with 9. Okay, so that's the 3 possibilities here, right? The middle one is the tough one. I mean, the top one is kind of trivial, right? You've got to take that, square it, and then multiply those two together, right? If the radius of a sphere is doubled, then the surface area is? Radius is doubled, surface area is?
Oh, no, it's just, isn't it just double?
We haven't even been in the same room for 2 days. Come on, give me a word.
Surface of square is.
What's it multiplied by? Yeah, 4. So what's the word for 4? Quadrupled. So if the radius is doubled, then the scale factor is 2. Then the surface area is the scale factor squared, which is 2 squared, which is 4. So this is quadrupled. And the volume of the sphere is multiplied by? I don't care. Somebody say the right answer off the bat.
6.
No.
8. 8. Oh my god. I'm on the wall.
Yeah, I know. I accidentally touched up there. Now I've got to change the thickness. But it's okay for emphasis. If 35 milliliters of paint covered the original sphere, then determine the amount of paint to cover the scaled sphere. Is that a linear, an area, or a volume? It's an area. What are we going to multiply by? You got a choice of 3 numbers. So what are you going to multiply by? Come on, Jonas. Save us. Okay? So the surface area, if the linear is double, the surface area is double squared. 2 squared is 4. It's quadrupled. So if you need 35 milliliters of paint, you're now covering a quadrupled surface area. You need 35 times 4. Okay, or 140 milliliters. If the sphere's scaled volume was 80 cubic centimeters, then determine the original volume. Okay, scaled volume is 80. What was the original volume? It's like I'm just pulling numbers off a page.
35.
Yeah, which is the number that has absolutely nothing to do with this. But
80. 80 is the number that has something to do with
80 is the number that has something to do with this. And what number up top of this is doubled, this is quadrupled, and the volume
8.
is multiplied by 8. So if the scaled volume is 80, the original volume is 10.
My neighbor.
So the volume scale factor is 8, right? See up top. So the scaled volume is 80. So the original volume was 10. Man, the scale by factor 8. We doubled. Okay. So the question was, so the scale's bigger than the original? Yeah, so we took the original and we doubled its measurement, which means that its surface area increased by a factor of 4, which is 2 squared, and its volume increased by a factor of 8, which is 2 cubed. So if the new volume is 80, the original volume is 1/8 of that. Last example questions of this course.
Yay!
Volume of a cube is multiplied 8-fold. The surface area of the same cube will be multiplied 4-fold. Okay? So that's how you run the numbers. The volume of a cube is multiplied 8-fold. The volume scale factor is 8. The linear scale factor is the cube root of 8. Right? That's what I'm saying. So you're given the volume, you cube root it, you get the linear, you square that, you get the area. Okay? So just do it that way. It's not that hard, right? A spherical balloon is completely inflated. The air is let out of a balloon until the surface area is 1/9 of the surface area of the inflated. How does the volume change? You can do this in your head, honestly. Toss out a number.
8.
That's not that number. Okay, so before we put the vehicle in gear, we should put the clutch in first. Otherwise, there's a grinding sound and a lot of smoke, which is what I'm getting right now.
3, yeah.
So, let's just think of this. Before we even answer anything, if the area is 1/9 of the original area, will the new volume be larger than the original or smaller? It's going to be smaller. Okay, if the area was 1/9, then what's the linear scale factor? 1/3. Then what's the volume scale factor? 1/27. Okay, so you're moving from an area scale factor, right? I got an area scale factor of 1/9, which leads to a linear scale factor of the square root of 1/9 or 1/3, which leads to a volume scale factor of 1/3 cubed, or 1/27. Okay? So that's how you do it, right? If you get a volume scale factor, you cube root it to get linear, you square that to get area. So you're given an area scale factor, you square root it to get linear, you cube the linear to get the volume. That's it.